One of the things that has always distinguished calculus from other math classes is its ability to work with rates of change and its ability to work with variables that just change with respect to time. If calculus is anything, it's the study of rates and how these variables and these quantities change over time. Not everything in the world is static. Not everything in the world is constant. And so one of the beauties of calculus is that we're able to apply the mathematics behind it to help us study how things change with respect to time. And in this video, what I'd like to do is talk about the concept of related rates, which is maybe one of the most common ways that we see derivatives being applied in various real-world situations. It's a really important application of calculus. And to start this discussion off, I'd like to share with you an example. Imagine a stone or a pebble is being dropped into a pond, and it creates ripples. And as the waves, as the ripples kind of grow across the surface of the pond, the circles that you see are actually increasing in both the size of its radius and the size of its area. So here's the situation. The question says the stone is dropped into a pond and the circular ripples are changing. They're increasing as time passes. The radii, it is known, increase at a constant rate of 0.5 meters per second. If I were to freeze this animation, this is of course changing over time, but if I could just stop time at the instant the radius is exactly 4 meters, the question then becomes, find the rate at which the circle's area is changing. So here's how we're going to tackle these related rates problems. There should be a known rate, some kind of given rate in the situation. And in this problem, we know that the rate of change of the radius of these ripples, the circular ripples in the water, are changing at a rate of 0.5 meters per second. So r prime of t, which essentially would be the rate of change of the radius, I'm going to denote that actually like this. We'll call that dr dt. So that represents, that notation represents the derivative of r, the radius, with respect to time. Now, dr dt in this problem, we know is increasing at a rate of 0.5 meters per second. Now, the unknown rate. What is the question asking us to find? What is the missing rate? Well, the question says, at what rate is the circle's area changing? So if I use capital A to represent area, then the unknown rate would be dA dt, or the derivative of the area, the circle's area with respect to time. Now the condition, that's kind of this, again, this freeze frame moment. If I could just pause this animation and just stop time at the instant, at the moment when, here it is, the radius of the circle is 4 meters. So when r equals 4 meters, that would be the condition where we want to kind of stop or pause this situation that is changing. And then finally, we need some sort of equation that will relate these variables. So what kind of equation would relate the radius of a circle and its area? How about the geometric formula, area of a circle? A equals pi times r squared. So what we want to do now with these, with all this sort of organized collection of information, is write a derivative of the equation that we found. So again, implicitly with respect to time, notice that time is nowhere in the equation. I have capital A for area, I have r for radius. There is no t anywhere, but that's okay. We're going to write a derivative implicitly with respect to time. So here's how that is going to look. The derivative of A would just be 1, but again, it's implicitly so with respect to time. So we're going to call that 1 times dA dt. It's really the chain rule being applied here. The derivative of A is 1, but then times the derivative of the inside, which would be dA dt. dt is the denominator because it's with respect to time. Then a power rule over here, 2 pi r, that r, the power of 2 drops to a 1. And again, another chain rule times dr dt. So there's the implicit differentiation step for A equals pi r squared. Well, now let's plug in the various values that we know. We're hunting for the value of dA dt, so I'm solving for dA dt. At the instant that the radius is 4, is when I want to compute this rate. So 2 times pi times 4 times dr dt, which is the rate of change of the radius, and that was given as 0.5 meters per second. So plug in all the values that we know, and it looks like we'll have 8 pi times 1/2, or a final answer of 4 pi. And then what are the units now? What's the rate at which the area is changing? Well, the area of a circle is going to be in square units, so square meters, and then time was in seconds. So there we go. There's your first example of what a related rates problem looks like. Now, I'd like to show you a couple more examples, and at any point, feel free to pause the video and kind of read the question, see what you can determine on your own. I've got a worksheet with a couple of examples on it here. I think I'd like to do about 3 of them. So feel free, again, pause or fast forward the video so that you can be as successful as you can with your practice here. Let's begin with this example where it says street light shadow. So here's a lamp post, and it says there's a 6-foot tall man who's walking away from the light. So if we kind of draw, this sort of resembles a shadow problem from geometry. So we'll put the man over here, 6 feet, and the lamppost, the streetlight, is 15 feet tall. And let's see what we know here. Why don't we call there's a shadow here. The man's shadow is being cast down below. So let's call that shadow, what do we know here? Here's the shadow part. Determine the rate at which the man's shadow is lengthening. At the moment, he is 20 feet from the base of the street light. So if he's walking away from the street light, then I have variables down here. Let's call the shadow x, and let's call the man's distance from the street light y. So essentially, dx dt would represent the rate at which the shadow is changing, dx dt. And that's missing. That's my unknown rate. But then I know this. It says the man is walking at a rate of 5 feet per second away from the street light. So that distance of y in my picture here would be increasing. The rate, dy dt, would be increasing by 5 feet per second. So there's the known rate and the unknown rate. We're kind of building this triangle, or these triangle relationships, up as we go. Now I need an equation that relates x and y. So how about we use similar triangles? By angle-angle similarity, we have a right angle there at the base. The man is standing upright, so a right angle there as well, and then a reflexive angle. So these are similar triangles, which means I can write a proportion. So side x would correspond to side 6, as the long segment, x plus y, would correspond to the long height of the street lamp, which is 15. Let's cross multiply and solve. 15x equals 6x plus 6y. And if I combine like terms and work out some algebra here, I'll end up with x equal to 2/3 times y. So there's an equation that relates x and y. Now take the derivative of the entire equation. Well, that'll be dx dt equals 2/3 times dy dt. And we know dy dt is equal to 5. So let's plug in 5. And I'll have a value of 10/3. 10/3, the units would be feet per second. That's dx dt. It's positive because the shadow would be, or the rate of increase in the shadow is increasing. So 10/3 feet per second would be that solution. Number 2. Actually, I'm going to skip number 2 since we did a radius and circle problem already. Let's look at number 3. This one says rising balloon. A hot air balloon is rising straight up from a level field. Okay, so I can call this distance maybe h, the height of the balloon. And what else do we know? It says there's a rangefinder 500 feet away from the liftoff point. So I've got a fixed rangefinder down here, and that's 500 feet away from the point where it took off. The angle is increasing at a rate of 0.14 radians per minute. So d theta, if I call that angle theta, d theta dt, the rate of change of theta, the angle with respect to time, is 0.14 radians per minute. There's my known rate. What's the unknown rate? How fast is the balloon rising? So that would be dh dt. What is the value of dh dt? There's my unknown rate. So now what I want to do is somehow relate h and theta with some sort of equation. What equation out there, a geometry equation, maybe a trigonometry equation, an algebraic equation? Well, how about we use trigonometry? I have an angle, and I have a side opposite and a side adjacent. If I think about SOHCAHTOA, that's going to sound very much like the tangent ratio. So the tangent of theta is equal to opposite over adjacent. And remember that h divided by 500 is the same thing as writing 1 over 500 times h. And from a calculus perspective, I kind of like that a little bit better. And you'll see why in just a minute. So there's the equation. Let's take the derivative of both sides. What's the derivative of tangent? That would be secant squared theta, times d theta dt. Chain rule. The derivative of 1 over 500 times h would be 1 over 500. Chain rule. Times dh dt. So what else do we know here? We're looking for the values. In this case, it says here, at the moment, the rangefinder's elevation is exactly pi over 4. How fast is the balloon rising? So what we want to do now is plug in that pi over 4. So let's do that right here. As a matter of fact, we're looking for dh dt. Maybe it might be better to isolate that dh dt. Let's multiply both sides by 500. So we'll have 500 times secant squared of theta, but we're going to plug in our theta value, which will be fixed at pi over 4. It'll be frozen or paused at pi over 4. D theta dt is given as 0.14, and all of that is equal to dh dt, which is the exact rate that we're trying to find. So with a little bit of help from maybe your calculator, some computations, the hope is that we will end up with a value of about 140 feet per minute for dh dt. You can check that with your calculator and see if that does in fact make sense. So there's an example with trigonometry. We saw one with geometry and area, and then we saw one with similar triangles. I have one final example for you, and it's right here, number 4, the sliding ladder problem. And this is one, again, another geometric application. We have a ladder that's leaning against a wall, and it says it's sliding down toward the floor. So here's the ladder. It says the ladder is 5 feet in length. That 5 is fixed. So we're going to call it 5 and keep it 5 for the duration of the problem. The foot of the ladder is sliding away from the base of the wall at a rate of 3 feet per second. Let's call this A, and we'll call the distance from the top of the ladder to the floor B. So what I have here is this right triangle relationship, an a squared plus b squared equals c squared Pythagorean theorem relationship that is about to take place here. So if the ladder is sliding outwards, then dA dt is going to be increasing by the rate of, what do we know here, 3 feet per second. There's my known rate. How fast is the top of the ladder sliding down the wall? So dB dt, again, according to my diagram, you could use any variables you wish, but in my picture, dB dt is the unknown rate that I'm hunting for in this related rates problem. And the freeze frame moment here is when the top of the ladder is exactly 3 feet off the ground. Well, when that happens, when b is equal to 3, then by Pythagorean theorem, a must be equal to 4. So we'll use those in just a little bit. Let's use a squared plus b squared equals 5 squared, because that hypotenuse, which is the ladder, is fixed at 5. And now we'll do calculus. The derivative of a squared is 2a times dA dt. Chain rule, because we're talking about this with respect to time. 2b times dB over dt. And then 5 squared will have a derivative of 0 because it's a constant. Let's plug in what we know and solve for the unknown. 2 times a, we're going to freeze this animation when a is equal to 4 and when b is equal to 3. dB dt is my unknown rate. I'm solving for that unknown quantity. So this looks like I'll have a 24. Actually, let's subtract 24. So 6 times dB dt equals negative 24. Final answer for dB dt, draw that up here, is equal to, divided by 6, so negative 4. What are the units? Negative 4 feet per second. And it's negative, which means that segment B, the distance that represents B, is decreasing, which should make sense intuitively, because as that ladder falls, the distance from the top of the ladder down to the wall would be decreasing. So the negative on that derivative helps me recognize that what I found here was a reasonable solution. So that's pretty much how related rates work. I hope these examples are helpful to you. It's going to take practice and it's going to take some time. Make sure you label the variables that you know and that you don't know, and do your best to try to organize your work as much as possible. But these are really powerful applications of calculus and the derivative, specifically implicit differentiation with respect to time. So good luck as you try a couple related rates problems.